Excellent, thank you. Okay, let's get things started. After an exciting round of talks this morning and some interesting climate discussions, pleased to welcome you to this parallel session where we've got a bunch of exciting talks planned. So each talk is 12 minutes with 3 minutes of questions. It'll be an action-packed adventure. And to kick us off, I'm really excited to hear about Lennart Balkenhol's talk with SPT-3G. Tell us all about these exciting results. Take it away.
Thanks, Tamara. For those of you who don't know me, my name's Lennart. I'm a PhD student at the University of Melbourne under the supervision of Christian Reichardt, working on data analysis of the South Pole Telescope. So I'll kick things off today with a brief introduction to cosmology and in particular CMB science focused on the South Pole Telescope. I'll then transition into talking about cosmological constraints from our latest data set, SPT-3G 2018 EETE, and hopefully that acronym will make a lot more sense in a moment. We'll break this up into looking at lambda CDM, so the standard model with a focus on the Hubble tension, and then taking a peek beyond lambda CDM before concluding. So let's get started. As you know, after inflation, the young universe was hot and dense. Photons frequently Thomson scattered off electrons, effectively making the medium opaque. However, after around 300,000 years, just through expansion, the universe was able to cool enough for neutral hydrogen to form. In this event, which we call recombination, the cross-section for Thomson scattering was dramatically reduced, which effectively meant now the universe was transparent. The photons that originated then at what we can understand as the surface of last scattering can travel more or less unimpeded through the universe to us today. We observe them redshifted into the microwave part of the electromagnetic spectrum, and hence the name cosmic microwave background, or CMB. The CMB originating from such a high redshift when the universe was really young is rich in cosmological information. It essentially paints a picture of an interplay of pressure and gravity waves. We can see sound waves ripple through the CMB when we take really detailed pictures. It's not only rich in information in temperature, which we commonly abbreviate as with T, but also carries lots of information in polarization. We usually represent this using using a basis of B modes. So the sort of bread and butter CMB analysis you do is you take a picture of the CMB, which you call a map, such as the one shown on the slide here made by the Planck mission, and you look at certain correlations at different angular scales, so power spectrum analysis. Doing this has really helped us determine the cosmological parameters of the standard model to within percent precision and even better. And CMB data has really been a cornerstone of modern cosmology. But despite the success, we kind of know that it's not the full story. Some things don't really add up. Lambda CDM is great, but it doesn't really tell us anything about the nature of dark matter or what dark energy really is. We also haven't measured the mass of neutrinos yet, despite really trying to do so. And we're plagued with a few intriguing puzzles in our data, such as the Hubble tension and some similar behavior maybe in another parameter we call S8. Nonetheless, the polarized CMB is a great place to look to pursue these questions. That's because CMB polarization is actually more rich in information than CMB temperature alone. It's also less foreground contaminated. So we have the potential of observing smaller angular scales here, which again still carries some valuable information. And this is where the South Pole Telescope comes in, which observes the polarized CMB. It's a 10-meter telescope, and as the name suggests, it is at the geographic South Pole. It's hosted 2 surveys in the past, but the current one is called SPT-3G. It features 15,000 polarization-sensitive bolometers, which observe the CMB at 3 frequencies. It's essentially relentlessly scanning a 1,500 square degree field, the footprint of which is in the picture here. The goal is achieving a map depth of 2 microkeV arc-minutes, and we started observing in 2017 and hope to continue through 2023 to achieve this goal. So even though we started kind of recently and still have a few years of the survey to go, we've already analyzed our 2018 data. And this alone is rich in cosmological information. And we're really proud to publish our first power spectrum analysis at the start of the year. Now, this is an EE and TE power spectrum analysis. So calling back to what I said earlier, it's the E-mode polarization autocorrelation spectrum and the temperature E-mode cross-correlation spectrum. These are shown in the plots on the slides here with the EE spectrum at the top, TE spectrum at the bottom panel. The horizontal axis, labeled here as multiple moment, is essentially just different measure for angular scale, with small angular scales living to the right and large angular scales living to the left. You can see that there's some beautiful wiggles in the power spectrum, which call back to these sound waves that ripple through the early plasma of the universe. To give credit where credit's due, I did not produce this power spectrum measurement. This was carried out by Daniel Dutcher at UChicago. So we have got this really great new data set. Let's do some cosmology with it and see what we can learn about the universe. For Lambda CDM, we find that our new SPT-3G 2018 data set is super consistent with it and really likes it as a model. The cosmological constraints are largely consistent with those of other contemporary CMB experiments, such as Planck. So let's cut to the interesting bit. Let's look at the constraint on the Hubble constant, so the expansion rate today. The result from SPT-3G alone is around 69 kilometers per second per megaparsec, which you can see in the plot given here as the top data point in black. This is essentially consistent with the Planck data set, which you can see as the gold data point just beneath, as well as the latest data from the Atacama Cosmology Telescope, which is another independent ground-based CMB telescope, shown in the plot here in green. Now, this is quite a strong statement from the CMB side, given that these three data sets are essentially independent of one another and derive their constraining power either from different parts of the night sky or different angular scales. And yet we do find consistent results for H0 here. Seeing as the data sets are largely independent, we can combine them and obtain a combined constraint without worrying too much about the correlations between them. Doing this, we get the red data point shown here, which is the tightest H0 constraint from the CMB to date, 67.49 plus minus 0.53 kilometers per second per megaparsec. Now, if you've listened to any cosmology talks in the last 10 years, you know the story doesn't end here. I have to talk about lower redshift measurements. Given the time constraints, I will only focus on the distance ladder analysis of Cepheid and supernova data here, which also happens to give you the most precise low redshift anchor point. So this is done by Result 2020, the SHOES team, with their latest and most precise results shown in blue here, which comes in at 73.2 plus minus 1.3 kilometers per second per megaparsec. You can see just how glaring the rift to the CMB side is in the plot here. If you quantify it, it's just over 4 sigma. I wish I had a better way of ending this slide other than to say the H0 tension is alive and well, and I don't have a way of solving it. So let's move on and take a look beyond Lambda CDM. Now, with the CMB and with our SPT-3G data set, we've got a good chance of constraining some popular extensions to the standard model. So this is an explicit search from new physics. In the associated paper, we've considered a whole array of cosmological models. Unfortunately, I don't have time to go into each and every one today, so I've only picked out my favorite for you today. Please do check out the paper if you want to get the full story. But today I'll only talk about an effective and YP. What does that mean? Well, an effective is the effective number of neutrino species. In the standard model, this is usually 3. YP is the primordial helium abundance. This is a bit more tricky. It depends on the baryon density, and if you vary an effective, it's also a function of that. But suffice to say, it's usually 0.25. Why would you vary these two parameters? Well, they're actually quite a flexible probe of the energy density in the early universe, and as such sensitive to any particles that transition from the relativistic to non-relativistic regime between BBN and recombination even afterwards. So we can catch any sort of particles smart theorists come up with here, like axion-like particles, hidden photons, and the like. Our SPT data is particularly great at constraining these models because they tend to show up in the small scale anisotropies of the CMB, where the properties of the South-Pole telescope really come in handy. But enough of the model, let's look at the constraints. So from our SPT-3G 2018 data, this is the result we get. N effective of 5.1 plus minus 1.2, and a helium fraction of 0.151 plus minus 0.06. These are two around 1.5 sigma away from the standard model predictions. It's a little bit easier to see in the plot on the right. It's a little bit busy, but I'll walk you through it. The dotted horizontal gray line corresponds to the standard model value for an effective of around 3. The gray horizontal band corresponds to a galaxy-based measurement of the primordial helium abundance, Balkenhol 2020. The black line corresponds to BBN consistency. And then on top of that, the colored contours are your different CMB experiments. You've got your constraints from Planck in gray, from the Atacama Cosmology Telescope in blue, and then from the South Pole Telescope in red. And you can see that, yeah, it does scatter a lot to the right and to the bottom, higher values of ineffective, lower values of the helium abundance. However, we are not making a claim of a detection here. This is not evidence from new physics, and I want to be explicit about this. There's a number of reasons we think this is more consistent with a statistical fluctuation in our data. First of all, extending your standard model by 2 new free parameters now makes it 8-dimensional. So a couple of 1.5 sigma fluctuations are cool, but they're nothing to write home about. Moreover, it's also worth noting that the chi-squared of the best fit doesn't improve really compared to lambda CDM, at least not as much as you'd hope by introducing 2 new free parameters. So I'll wrap things up here. I hope I could convince you that SPT-3G already places some tight and interesting constraints in cosmology. We started out by looking at lambda CDM and reweighed the Hubble tension. Using a new data set and the others available, we found it to be over 4 sigma now. We then detoured from that without solving the Hubble tension into looking at extended models. We only looked at an effective in YP and found an interesting statistical fluctuation here in the SPT data. As I mentioned before, this is only the 2018 data set from our SPT-3G telescope, instrument, and it's scheduled to observe through 2023. In fact, we already have maps on our hands 3.5 times as deep as the ones that went into this analysis. So really excited to dig into those and learn more about the universe. Thank you.
Excellent. Thanks very much, Lennart. That was a really interesting talk and cool results. I can already see one question here from Colin Howlett, who asks, he says, thanks for the very interesting talk. When performing the N effective plus YP fits, did you fix the sum of neutrino masses? Could some of the larger preferred N effective also be explained by changes to mu?
The neutrino mass is fixed to the minimum allowed by solar oscillation experiments, so 0.06 eV, I believe. We didn't look at a model that flexibly changes an effective mu, but we did look at some sterile neutrino models, which introduce a effective sterile neutrino mass to sample over as well as an effective. And here we did see that, yeah, again, we find slightly higher preference for an effective, though it does come with an increased uncertainty, at least for now. So it's quite difficult to say something definitive about these models as of yet.
Another one from Matthew Collers, who asks, what will the final 2023 constraints be on H0 and N effective?
I'm glad you asked that question.
He's not asking you to predict the numbers, but maybe the precision.
I do have a backup slide for this.
This is what I prepared earlier.
Here we go. The aim, the hope is that SPT-3G will constrain cosmology as well as back. There's a small caveat to here, NS, for example, where the large scale information is really crucial. But say for something like H0, we expect the same precision here. You've got a table of parameter errors for a few cosmological parameters with H0. On the far side, you can see SPT-3G is essentially comparable to Planck. And of course, if you then take the combination of the two experiments, you get a even tighter constraint.
So one last quick comment, I think, before the, or question before the thing, when you claim that H0 tension is alive and well, you should work of Friedman. showed the locally determined value of H0 based on a new tip of the red giant branch calibration was 69.8 plus or minus 1.6. Any comment on that? I know that was like something that was about 2 years old that's now got a recent reanalysis of and ended up with a similar number.
I'm certainly aware of the work, and you can semantically argue that maybe Hubble tension isn't the right word, and you really want to label it as a tension between CMB and Cepheid and supernova probes of H0. You can make a similar argument by looking at the TD Cosmos results and other probes of H0. We've simply focused on the SHU stim here because for now, they do still provide the most precise H0 measurement. But you're correct in pointing out that other H0 measurements from low redshift data are available, and they're very quickly reaching the precision to allow us to make some really strong arguments here.
Excellent. Well, thanks very much. I think we better move on. So if we can thank Lennart again, and if you unshare your slides, our next speaker is Cullen Howlett, who's actually just across the hall from me here at University of Queensland. Take it away, Cullen.
Yes, hi everyone. Thanks. Let me see if I can share my screen. Okay, can you all see that in not presenter view?
No, that's in the presenter view, so switch screens.